So thank you everyone for joining us for today's office hour, which will be led by Dr. Rich Gonzalez. Rich is the director of the Research Center on Group Dynamics here at the University of Michigan. He is a psychologist, data scientist, statistician. The reason I love working with Rich is that he has an incredible ability to explain really complex things in a way that I can follow and use. And I know that that is what he's going to do for us today as he gives us a gentle introduction to data science. And with that introduction, Rich, I'm going to turn it over to you.
All right, thank you. Could you make me co-host or is already okay? So let's see. Hmm. Let me check one thing first before I start showing things. Oh, sharing the wrong one.
It did not look like a gentle introduction, Rich.
No.
It looked like a very serious.
There we go.
Oh, love it.
All right. So Bree asked me to do a gentle introduction to data science. And as I planned what to say, I thought maybe the best thing I can accomplish in the hour that we have is just to establish some vocabulary words so that when you hear terms like sparsity, regularization, deep learning, features, and these kinds of things, you at least have a sense of what people are talking about. And along the way, I'll highlight some conceptual differences in terms of goals and objectives that people have when they analyze data. From a traditional statistical approach or from a machine learning data science approach. So for some of you, you might already be familiar with these terms, and that's great. But Bree was telling me that I should not assume much beyond a knowledge of regression. So that's what I'm doing today. So the outline is I'll talk a little bit about what is data science, kind of why data science, and I'll give some very intuitive examples of how data gets analyzed and visualized from the data science perspective. And then I'll highlight those perspectives and compare and contrast them to more traditional ways that you might see in published articles that use regression and statistical hypothesis testing. And then just summarize with kind of hitting those vocabulary words again and presenting them as almost tricks of the trade. So let's go right into the, I skipped way too much ahead. Okay, the title is You Say Features, I Say Variables. And this is one of the vocabulary words, is that in statistics and biostatistics, we talk about variables, there's predictors and dependent variables. And in data science, they don't use the word variables, they use features, but they basically mean the same thing. So it's an example of what I mean by getting the vocabulary down. And I'll highlight some of the subtle differences and why maybe data science likes to use the word features rather than variables as we progress. So this is a slide that I presented last summer when I gave a short presentation around causal methods at the MeWe in-person meeting. And this quote basically says, the goal of science is not prediction and control, but understanding. Prediction is merely the test of understanding, and control the practical reward. And when we work on results sections and papers, we tend to forget that the real goal of writing the paper is to contribute new knowledge and understanding to the problem we're tackling. And we get wrapped up into all the details of how we analyzed our data and our sampling strategy and sampling weights. And tables that we present and so on. Um, Similarly, when we think about data science and statistics, we tend to focus on very different aspects of the problem that aren't necessarily understanding. So as you'll see in today's gentle introduction, data science tends to give more weight and attention to prediction at the expense of understanding. So in data science, you're perfectly happy to say, I simply do not know how the model works, but because the model makes very good predictions, I can use it to make predictions. And so therefore it's valuable, even though I don't understand how the model works. And in some cases, it's impossible to understand how the model works. And I'll explain what I mean by that. In other aspects of data science, we care about being able to control things, like the randomized controlled trial and having double blind. And we're very concerned about the design of the study. And again, control is not the goal of a study or, of our scientific work. The goal of our scientific work is to understand the phenomenon that we're after. Control is just one way that we can conveniently rule out alternative explanations and make some of our inferences a little bit easier compared to alternatives of observational data where we may not have the ability to control for confounders and so on in the way that a randomized controlled trial does. So both in statistics and in data science, those fields tend to lose sight of the fact that the ultimate goal of our scientific work is to produce understanding. And instead, if you're data science, you focus on prediction primarily. And if you're in the world of regressions and experiments, you focus on control. And control could mean different things. It could mean, all the covariates you have in your regression equation. Control could be you do a randomized controlled trial or a bunch of other methods to deal with causal inference. So this is like a way to organize the rest of my comments in the remaining 40 minutes or so. So machine learning does a spectacular job at predicting things. And if you've ever used ChatGPT, you should be impressed with its ability to produce prose based on prompts. Like you ask a question, and it can produce paragraphs. And it's simply a predictive model. It just shows you how useful and impressive a simple predictive model can be, even though we don't have any possibility of understanding how exactly that model works. Now, when what you want to do is go after prediction at all costs and be able to have the best predictive model, what you can fall into, traps you can fall into are something analogous to teaching to the test, right? So in grade school, if there's a standardized test, teachers might be incentivized to just teach to the test so the students get the highest score possible and not care about whether they comprehend the material. Something analogous happens in data science, where if what you care about is prediction, you might, in a sense, be developing models that are analogous to teaching to the test. All they do is predict, and you might do things that look very strange to someone that doesn't come from the data science tradition. So, for instance, one thing that you can do to improve predictive accuracy is have many models and not worry about which model is right or best, but take all models and average them. And that now gives you a better prediction than any model alone. So I'll give examples of that later today. If you don't care, if all you care about is prediction and you don't care about trying to understand the model, you can grow the number of parameters to have millions or billions of parameters. So think about a regression equation that has billions of beta coefficients. It's impossible to try to understand that regression equation because you can understand a billion betas. That's exactly what deep learning does. So ChatGPT has billions of parameters analogous to betas in a regression equation. And if what you want to do is predict, you can let the number of parameters grow. Something else you can do is you can tinker with your variables, your predictors or features, as they're called in the data science. And you can create all kinds of versions of your data. You have your observed variable, your observed column of numbers, and you can create many transformations of those columns. You can say, well, I'll take the mean, the max, the autocorrelation of that time series. There's any number of things you can take all of them and try them out as predictors and see which ones work, because there might be versions of your data that you didn't think of that might predict better than the form the data were originally collected in. And that area of study is called feature engineering, of how should you construct your variables so that you can get the best possible prediction. Now, all three of those things that I just talked about go against I'm letting people in who are coming in. Okay.
Sorry, Rich, I can handle that. I'm sorry.
All right. Now, this goes against everything we were instructed by our statistics or in biostatistics teachers, right? We were told that the way to approach data science is you try to find the best model. You would never average all the models. You would never take the bad models and the good models and somehow piece them together and write your paper about the average of all the models. We are told that we should try to get as few variables in our regression as possible, right? Many betas is not always a good thing. We want to try to reduce the number of betas. And we've developed a whole bunch of tools like principal components and factor analysis to take multiple variables and reduce the dimensionality down to a smaller set of columns of numbers that would be like components or dimensions or factors of original data that were more complicated. And we're also told that we shouldn't tinker with our variables, that there's something sacred about the column of numbers that we observe, and we shouldn't try to re-express those numbers in dozens and dozens of ways to see almost like a fishing expedition, trying to see which versions of those variables might perform better at prediction, right? So in the 3 bullet points in black are exactly what data science shines and does very well, yet those are the same bullet points in red that we were told not to do. So that's the tension that I'm going to be talking about and kind of what makes the type of data analysis that appears in our journals different from data science. Along the way, I'll use some terms that I'll define as we go along, but I just want to throw out the terms so that you hear them multiple times. I'll talk about out-of-sample prediction, cross-validation, approximating functions, regularization, dimension reduction versus embedding, and feature engineering. Okay, so I'll define these as we go along. Now, why are we even talking about data science right now? We have the ability to collect data like on everything, right? So even there are cartoons in the New Yorker, get me everything on everybody. We, in a sense, have the possibility that our studies could be N equals all. Like every human on Earth could, in principle, be in our study, depending on the way that we, the data collection methods we have available to us, like smartphones and so on. So it's possible for N to be at a scale that we just have never seen before in any of our disciplines. we have the ability to have more predictors than we have data points. You've learned in regression that that's impossible. In the regression framework, you are limited to, you can't have more predictors than the number of subjects because you run out of degrees of freedom. You'll have negative degrees of freedom if you have more predictors than subjects. So regression can't handle that. But data scientist, gosh, you could have, 5 times the number of predictors than you have the number of subjects. So if you have 5 million subjects, you could have 100 million predictors, and with no problem. Our computing is now kind of unsurpassed. We have computer, like our smartphones that we carry in our hands, or watches that we have, are like more powerful than any of the desktops that were available when I was in graduate school. And so kind of computing is like at a scale that is just unimagined, you couldn't imagine just a few years ago. And we know how to handle data that are of different types. So not just numerical data like we learned in statistics, but we can work with data that are text. We can work with hand-drawn images, like, the clock drawing task that's used as one of the tests for diagnosing dementia, where you ask people to draw a clock and put the big hand and small hand so that corresponds to 11:10. And so the individual draws a clock, and now we have ways of analyzing those hand-drawn images. So there's ways, kind of the technology has progressed where we can take information and collect it and use it as data, and that information doesn't even have to be numeric. We're also able to handle data at a velocity that is just remarkable right now, right? There are devices that collect data, 1,000 data points per second. Some of the smartwatches are collecting data at a rate, similar to that. And storage has become pretty cheap. It's easy to get data. We can scrape data off the web. We can, give people smartwatches and download their data. We can pay Apple and get access to all the data that Apple collects from their users. And similarly, from Android users, we can collect data. You can go to Zillow and pay Zillow to have access to all their data that, in terms of the housing market, and start linking up these different data sets. So a subject comes into your lab. If you know their address, you can connect to their Zillow site, and you instantly know a whole bunch of things about their house, like the number of bedrooms and whether they're on a sewer system or a septic, and, a whole bunch of information, the number of bedrooms. And then you can link up to their medical records. You can link up to their IRS. The ability to start interleaving massive amounts of data on individual people is unprecedented. And all of this is kind of what's making data science so exciting, and why everyone's talking about it. As I hinted in my initial comments, data science sometimes has different goals than more scientific goals that you would see in journal articles. So here's a quote from a former director of New York City's analytics department. He said, "I wanted actionable insight, and that's all I cared about." So he didn't care about whether it was correlational data or whether the data came, was a representative sample, or whether the controls were in place, or, he just simply said, "You have all this data on people in New York City. Give me things that I can act on, that I can create policy about." And all the things that we're trained as scientists to think about, like measurement error and study design and sampling and confounding, like all that gets ignored in data science. You might be thinking, as I'm kind of making these distinctions, that wouldn't it be great to have a hybrid? Like, why can't we take the best of both worlds, the best of data science and, the best of how we operate as scientists and create a hybrid. And that's the direction that everybody is moving toward, but it's going to be many years before we get there. Right now, it is pretty much this either or distinction that I'm characterizing. So let me start giving some examples. And the first thing I want to do is direct you to a couple of books. The book on the left is a little bit more user-friendly in the sense that it's written with applications, lots of examples in R, and they're companion versions. There's the same book, but written for Python. And this just goes through many of the techniques of how data scientists work using a package that you would use in statistics as well, R. And if you want more of the theory behind it, then it's the companion book on the right. These are both classic books now. And so if you want to learn more about the things I'm talking about, those are great places to start. So let me give you an example of how this very counterintuitive idea that's the opposite of everything we've been told as behavioral scientists. So I was trained in graduate school that if I have a scale of many items, rather than trying to work on the individual items, I could run a factor analysis or principal components to reduce the dimensionality, right? That maybe my 10 item scale is really one dimension, or it might be two dimensions. And instead of working with the 10 original items, I can reduce the dimensionality. And a lot of what we've been taught is that dimension reduction. In fact, like regression can be thought of as reducing the dimensionality. You have lots of predictors and you're trying to find out which predictors are significant and not. And so you're reducing the dimensionality of which predictors you should continue to consider in your work, right? Because if a predictor consistently comes out as not being significant, then it can be dropped from consideration as we develop theory and progress our fields, right? So there's a sense in which regression is itself reducing the number of dimensions. And everything that is part of statistics and biostatistics is all about reducing dimensions, making everything simpler. But let me give you an example of how sometimes we can make a problem simpler by increasing the dimensionality. By actually making it more complicated, the problem becomes simple. And so this is the textbook example of what I mean. Suppose that we have to classify two different kinds of people. There's a group of people, and we're going to denote them in blue, and a different group of people, we're going to denote them in red. And so an individual is binary. They're either in the red group or in the blue group. And there are two predictors, X1 and X2. And both X1 and X2 are continuous, right? So it could be like age and BMI or something. There's two things that you know about individuals, and your goal is to classify them. Is this individual, given their BMI and age, are they in the blue group or in the red group? It turns out that this particular data example is extremely difficult to develop a classifier for, because the blue dots are in the center and they're surrounded by the red dots. So the red dots make like a larger circle around the blue dots. There's no simple line that we could draw that could classify that if you're on one side, you're in the red group, and if you're on the other side, you're in the blue group. Actually, it's a really complicated classification problem. Logistic regression cannot solve this. There is no logistic regression problem that can tell you, if you know X1 and X2 as the two predictor values, what's the probability someone is in the red group or in the blue group. But what we can do is, and I have to switch to a different screen. So this is the one that popped up initially that looked scary. So what I want to show is that that circle, that's impossible to think about how you could develop a classifier that produces tells you a blue or a red individual. If we took that two-dimensional plane and turned it into a three-dimensional surface, it turns out that a simple classifier emerges just naturally. And so here's a little video of that. Do you see a video?
Yes, we do.
Okay, so the blue in the middle and the red. So let's take that plane, and now we're going to move it into three dimensions. So there's a vertical dimension now, and now all the red dots are above the blue dots, and it's possible to make a cut through that surface. So all the blue dots are on one side and the red dots are on the other. So we've now have made a complicated problem simple. And now once you have that solution in three dimensions, you can bring it back down to two dimensions, and the classifier is the circle. And if you have the formula for that circle, you can classify people into being either in the red group or in the blue group by just knowing their two predictor X1 and X2 scores. So a problem that was initially very difficult when we looked at it in two dimensions, by making it more complicated and going to three dimensions, it became instantly solvable because we can cut the space, cut the surface, so that all the blue dots are on one side and the red dots are on the other, because that's what a classifier does. A classifier simply cuts information, and it says, if you're on one side, you're red, if you're on the other side, you're blue. So in three dimensions, that classifier was trivial. And then once we have it in three dimensions, we can project it back into the original space we were in, into our two-dimensional space. Any questions on that?
Rich, how does that extension to the third dimension happen in that case?
How does what?
How I guess, can you talk through on what was the math that happened
Oh,
that created that third dimension?
just a polynomial. So if I had added, for instance, an x squared.
Yep. Okay. That's what I was.
That alone gives me that's like saddle shaped kind of figure. But conceptually, what the tension here is between, we were been always told to reduce the number of dimensions, but sometimes increasing the number of dimensions, in other words, adding more predictors, adding an x squared term, can make the problem easier to solve. So even though we added another like beta in our regression equation, another term, the original very difficult problem now becomes very easy for that regression to solve as a classifier. So the point of this example is simply to show that maybe we were misled, that it isn't always better to reduce the dimensionality of a problem, that there are cases where making something more complicated actually provides insight into coming up with a very simple solution, that we couldn't see that simple solution when we were looking at it in the original space that the data were in.
Rich, can I ask one question based off that? So is there any information at this point to be able to discern when it might be a good idea to make it more complicated? I guess that's one of my questions. And then, or is it more of a play and see? No, I don't know if that's the right language to use, but play and see what helps to make it more understandable.
The data science answer is both.
Okay.
Actually, you play by allowing everything you can possibly think of and throwing it into the mix. And then the algorithm starts deciding what's useful and what isn't useful. So the human is not part of that algorithm of deciding what should be in or what should be out. The human just says, let's think of every possible thing we could throw in and throw it all in. And then the algorithm will start saying this just is irrelevant, 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 and eventually it'll whittle down to something that is more manageable. That the best thing we can do to initiate as a human kind of data analyst, the best thing we can do is give the algorithm as much information as possible and let it decipher what information is in all of that data. And by data, I don't just mean the rows in a spreadsheet, like, like more people, also the columns. We can just start having, adding more columns. So if you have a column X like age, add age cubed, add age squared, the square root of age, the average age of the people that live in the zip code, right? You just start adding everything you can possibly think of about age. And the more the merrier, just like throw everything in. And the more creative you are, the better possibility the algorithm has to find an innovative solution to that problem. Because the algorithm can't necessarily take the columns of data and re-express them naturally. It can simply say, given the columns of data it was provided, how can it optimally combine that information and decide what's useful and what isn't? So it means that the task of the data analyst is now to like be creative and think of all the different pieces of information you could throw into the mix and not be shackled by, oh no, we can't do that because that's not quantitative information. It's a hand drawing. Like, no, if you can put the hand drawing in and there's a way to include it, throw it in. Right? That it's very liberating almost. And somewhat in the spirit of kind of some aspects of qualitative analysis as right as all right, well, let me kind of move on, because now you might say, well, wait, if you're able just to throw in more and more variables, we've also been taught about overfitting. We know that as you add more variables in a regression equation, the regression R squared is going to get better and better. It's going to get closer to 1, right? The more variables, eventually the regression equation might get an R squared of 1, perfect prediction. But that regression is, we've been told, is tailored only to the sample, that you overfit the sample, but you may not be able to generalize those conclusions about that regression outside of your sample. And that's one of the reasons why we're told to have very few predictors. Well, the way that data scientists solve that problem, because they allow you to have as many parameters as you can think of, they basically do an iteration between taking, for instance, a sample of your data, fitting the model, and then seeing how well that model predicts data that is kept in reserve, that it hasn't seen yet. And that's the generalization part that data scientists do well. So it says, like, suppose you had 1,000 subjects. The algorithm will say, I'll take 700 of the 1,000, I'll fit the model, and then I'll see how well that model predicts the data of the 300 that it hasn't seen yet. And if it didn't do well, it knows it has to go back to the drawing board. It has to tinker. And then it does it again. And then sees how well it predicts the out of sample. And now you have a tug of war between letting a model grow in terms of the number of parameters, which left by itself, it would just have more and more parameters, with a constraint that that model has to do well out of sample. It has to predict outside of the data that it was used to sample. We never do that in regression. In regression, we use all the data we have. We compute our slope and intercept. We write up our paper. We never ask, well, how well did that slope work on data that that regression model hasn't seen yet? Right? So this is the idea of cross-validation that I think in statistics, we have a lot to learn from. We have a lot to benefit from this idea of, when we write a results section, we shouldn't just talk about the sample we have, but we should sort of check to see how well that works out of sample. And it doesn't mean you have to go out and collect more data. You can just do this, keep some data in reserve, that the model hasn't seen yet, and then you can try out the model on the data that you've kept in reserve to have a test of how well it performs out of sample. So that's one way in which data scientists can reduce the dimensionality, right? Because if you have the ability to let the parameters grow, and now you need something to kind of cut it back. And what makes it, the way you cut back parameters is by penalizing a model when it does not perform well to predict out of sample. So I'll talk a little bit more about that. Let me give you a visualization of what I mean by feature engineering and how if you think of data in one way, you might not actually understand what the data are trying to tell you. So here I have two time series. I'm purposely not going to tell you what they are for a minute or two, but just think of it as have two dependent variables that I measured on a single individual. And I have it's like say 3,000 seconds. So every second I measure something about that individual, and the first time plot is the first dependent variable, and it seems to like start off low, and then about 1,500 seconds into the study, it goes high, right? And then it goes back to baseline at the end of the study. The second dependent variable, it's the same time points, and this one seems to have a little bit more of an up and down pattern where it starts relatively high, it goes down to about halfway, stays there for a while, then goes up to the max and drops down to the bottom, and then goes up to about baseline to where it started. So these are two different dependent variables over time. You might try to kind of come up with a story about what's happening between them. But I want to argue that the way these data were collected, which you don't know yet, it's impossible for us to understand what those data are trying to tell us through this graph. And this is the graph that everyone would do if you had data over time. You know, you have time series and you have two variables over time. Everyone does this plot and publishes this plot, does analyses on these data. All right, now let me tell you what they are. This was me on a run around a lake wearing a smartwatch, and the dependent variables are the latitude and longitude of the position I was in. So this is the actual data because at any given time point, I was in a particular longitude, latitude location. So I started in the upper left, that's where the parking lot was. I got out of my car and I walked down the trail, and then I turned left, and then I hit the lake and I ran around the lake. And so in terms of going east, west, north, south, um, I started east, I went west, and I came back east. That was the first time series that showed I started low, went high, came back to low, because I started east, went west, came back, or sorry, I said it the other way around. I started west, went east, came back to west. And then the one that was like up and down, I kind of, started north, went south, then stayed at the same level for a while, then went north and then all the way down to south and then back up. And that created what looked like the second one. Now, putting it together as me actually moving around the lake, that's the path that I actually took. And my point is, by representing the numbers in a different way, by representing them as the two dependent variables on the axes, and time is not anywhere in the plot. You have a different understanding of what these data are telling you. The normal way to do the plot is to say each dependent variable gets plotted against time separately, but you have no way of knowing how those two variables interact with each other and what information they're jointly trying to tell you in the way that if I look at my data this way. Okay, and then here it is superimposed on a Google Earth kind of image, the path that I took around that lake. Okay. Okay, I'll skip all that. The third kind of point I want to make about visualizing data, and particular longitudinal data, is here are some data from a project I've been involved in for now over 20 years. It's about studying the effect on a family of the birth of the second child into the family. So there are two parents and what's an only child up until that point. And then the parents have a second child. So now the older child becomes a sibling, right? So the transition to siblinghood is the way you can think about it. And what we've noticed is that there are different profiles of responses of the older sib to becoming a sibling in terms of the aggressive behavior that they show, in particular about a month after the birth of the second child. And so you see that there's this green color, this kind of, it starts off low, it goes up, then back down. So there's like an outburst of aggressive behavior. There's another group at the very bottom that just sort of stays pretty flat. The slope is essentially no different from zero, even though it looks like there's a positive increase. But there are two groups, the kind of magenta and the greenish group, that seem to show a little spike at like a month after the birth of the child in their aggressive behavior. So how do we get that? Well, first of all, those were means, and the means don't represent the variability in the data. So those 5 profiles of children actually have a lot of variability. So the 18 in that greenish group I showed you, they all seem to have that spike at 1 month, but they all vary in the nature of that spike and where they start and where they end. There's a lot of variability. And that group that was relatively flat is the group, the low stable group down at the bottom left. Right, a lot of heterogeneity, a lot of individual differences. So just looking at the means completely distorts all of that heterogeneity. So how can we come to understand it? Well, we can look at predictors. What predicts what places the kids in these 5 different profiles? And here we used classification and regression trees, which I don't have time to go into details of what they are, but they're basically a fancy way of doing regression in this data science way of we throw in a whole bunch of potential predictors that could, information you could collect while mom is pregnant with a second child. And could you predict which are the individual children that are going to show this aggressive outburst? And we had hundreds of variables that we explored. And it turns out that basically what matters the most is the temperament of the child. Is it an angry child to begin with? The quality of the relationship between the two parents. Most of them were heterosexual parents. And then how securely attached the older sib is to both the mother and the father. And the answer to those variables, the quality of the marital relationship, the temperament of the child, and the attachment to each of the two parents, basically identifies these 5 groups. So you could collect data while mom is pregnant with a second child, and this tree lets you make predictions about how likely the kid is to show an aggressive outburst a month after the sibling is born. And so far, the model is working pretty well. In terms of an analysis workflow, we have sort of multiple stages that we're exploring in this project. We have how we identify the predictors of these profiles that we're examining. I only presented the aggressive profile, but we have a bunch of other profiles around whether the child is withdrawn or shy, shows sleep disruptions, right? All the different behavioral issues that might occur while in the transition to siblinghood. So we need to identify a bunch of predictors. We need to identify these trajectories that the kids are in and distal outcomes. Like, how is this child going to be interacting with their sibling when the sibling is 2 years old? So we've been following these families longitudinally, and we have these data where we can sort of examine what's happening prenatal, a month after the birth, and then 2 years later, in terms of control behavior and sibling jealousy and a whole bunch of different behaviors. So this is a workflow that it doesn't fit naturally into the usual, you have one dependent variable, you have predictors. There, in a sense, there are three separate regression problems. There's one regression problem. We have to identify what are the key predictors that are part of our analysis. Another prediction problem, which is what are these trajectories, these profiles that we're looking at? And once we've identified the profiles, what do those profiles predict downstream, like 2 years later? So data science allows us to solve this kind of very analytically difficult problem, this kind of a workflow, like an analysis problem. Okay, this is a little kind of counterfactual exercise that I find very helpful when I explain data science to scientists. Let's imagine if famous scientists in history had data science available to them. What would they have done? So I'll give a quick example of Kepler and how he figured out the orbital motion of the planets around the sun, and Galileo. Galileo lived about 2 hours away from where Brianna is right now, 2 hour drive. So we'll start with Kepler. Kepler's famous contribution to science is that he gave us an understanding that the planets follow an elliptical orbit around the sun. And he did that through following principles of physics. He basically laid out a bunch of math and arguments about physics and made the case that planets like Mars will rotate in an elliptical orbit around the sun. What he had access to in terms of empirical data is Tycho Brahe in Copenhagen was very careful about collecting very specific data of the visible planets and where they were in the night sky. And these are the data that Kepler used to show the elliptical orbit of Mars. Very messy data with gaps, like there were periods where data were just not available. So this is from the year 1586 all the way to 1596. And how Kepler figured out the elliptical orbit there, I have no idea, right? But he figured it out from basic principles. Now, the vertical axis in this plot is the angle with respect to this coordinate system that's on the left of how high Mars is in the night sky. So 0 is about right here where the cursor is. And then, 50 is all the way at the top. Negative 30 is almost at the horizon. So if we look at the plot on the right, negative 30 is where Mars hits almost the horizon, the horizon, and all the way at the top is almost directly above us if you were to look straight up. So that's the information that Kepler used. And I trained a neural network model to the data that are available, and it does very well. It fits the data, and most importantly, it can take the data from the 1500s and predict where Mars will be in the night sky today at that observatory in Copenhagen. So it does really well at predicting. But here's the problem with that approach. And like Kepler would not have been famous if he had done what I did here. It turns out that if you were to follow Mars over from like February through December for like a year, the orbit in the night sky seems to do these little curlicues. See, so it starts on the far right. That's where February 17th and February 27th, right? It kind of moves along. And around October, it makes a little curlicue. Sorry, around June, it makes a little curlicue. So now by October, it was about the same place it was in June. And then it continues. So to the eye, when you're standing at the observatory in Copenhagen, it looks like Mars is like moving along the path, and it decides to make a little detour and like visit a buddy or something, and then kind of continue in its path that it was following. That's what these little things are. These little kind of changes in direction are and you see it up here in the far right in the upper, this little kind of change in direction. The machine learning model got those little curlicue patterns and figured out and could project them out to the year 2023 and does very well at making the predictions. What are those curlicues that are in the visible data? Well, it's because of where if Mars looks to us, depending where we are on Earth relative to the sun. So if you look towards the bottom, where Earth is, and you're standing on Earth and looking at Mars, Mars gets projected to like the back screen of the night sky. And depending where we're standing, Mars will project to the back of this night sky in a different position. And so if we're on, if it's like winter solstice versus summer solstice, depending what side of the orbit we're on, Mars will look to be slightly different, and sometimes we'll have these little curly patterns in the path. It's not that Mars actually followed that path, is that it looks like that to us because of where we are relative to the sun and Mars. Right? So it's an artifact of the data collection. The machine learning model worked with that artifact and was still able to make predictions, but the machine learning model didn't make the intellectual contribution that Kepler did, where Kepler identified the reason we observe those curlicue patterns is because of this retrograde motion artifact. And then he was able to eliminate it from the analysis and solve the elliptical orbits, which is not what the machine learning model did. The machine learning model just worked with the available data. So it would not have made the contribution, the actual contribution that Kepler did, even though it makes just as good predictions as Kepler does. And I don't have time to go into Galileo, but I can do the same thing for statistics, is that in statistics, you can take one of Galileo's studies where he was rolling balls down inclines to show the effect of gravity. And he would have determined that gravity impacts how fast a ball rolls down an incline, p less than 0.05. So again, he would have been able to publish a paper in our journals, but his contribution wasn't that gravity matters or there was an interaction between time and gravity. His contribution was to actually give us the physical principles that led to that. So regression is not the solution either. This is the point about the real contribution we have as scientists is improving our understanding. Now, some of the tricks of the trade, now that we're approaching hurricane season in the Caribbean, you'll start seeing more of these kinds of displays where there are many different hurricane models predicting where the hurricanes can hit landfall and at what time. And in the news, you'll hear the American model, the European model, this model, that model. And each of the models makes different predictions. Those are the red lines. If you were to average all those red models and get the white one, the green one is the average. The green one follows the actual path of the hurricane pretty well. So sometimes the average of many models, even if some models are bad, the average of all the models you have available is sometimes better than any individual model you have. So this is the example of ensembles or model averaging. And you pay attention to the news as the hurricane season starts to pick up. You'll definitely see this. I don't have time to talk about deep learning, other than to say that in deep learning, the approach is one of an hourglass, where you start with data that are represented in a very high dimensional space. You then reduce the number of dimensions down, And then once you've reduced it down, you go backwards and increase the dimensions in much the same way that I did when I added that third dimension to change the shape of that two-dimensional plane. So I know I'm kind of running out of time. Let me just finish by saying that one way to think about regression is that it approximates function. It's a way to approximate a function where a function is given a bunch of inputs, can you predict an output? And data science is doing the same thing. It's just function approximation on steroids because it lets you have as many parameters as you want. It lets you work with many functions that you average together. And it uses tools like cross-validation to help you narrow down the number of parameters and do this out-of-sample prediction that I talked about. So to conclude, the main thing that we can get from data science is that we can actually learn a lot of structure from simple observations. We just have to know how to look. And I'm hopeful that the future of how we do our science is going to take elements of both data science and statistics and give us some new tools to help us find that structure that's in the data. We just don't know how to look at and to find that structure. And then just to recap, if you want to make the best possible predictions about anything, if you're triaging emergency room patients and given information available at intake, what should you do? Data science is going to be the best possible thing you can do because it'll make the best predictions, right? Because you don't need to understand why, you just need to have action. You need to be able to know for this person, I should do this, for that person, I can triage, and so data science is great for prediction. If you want to understand something though, then data science alone isn't going to help you. But traditional methods may not be helpful either because there might be insights from the way data science views this analytic process that could help us get deeper understanding that we are unable to do with traditional methods. And I think I'll just wrap up there because I'm out of time.
Rich, thank you so much. This has been really fantastic. I wanted to say a couple of things just as we're leaving here. The first is that is it fair to say that the ensemble models is kind of the new version of like the wisdom of crowds, which is
yes.
the thing kind of this idea that even the people who have no idea how much a cow weighs, you ask 1,000 people how much does a cow weigh, and you average that together, you're going to get pretty much the right answer on that cow, and this is a phenomenon that's literally hundreds, if not thousands of years old, this idea, right? What I really love about the way that Rich explains things is this just kind of tying it back to these old ideas, and now we have different nomenclature, different jargon, but these ideas are not
right.
And then the second thing I wanted to say is that
just to build on that point, but think about how everything we have in our profession tells us we have to pick the best model. When you write your paper, your discussion section has to say, this is the best model given the information I have, right? Everything about what we do is picking the best when we are faced with this fact that there's information in the weakest models that if we could somehow figure out how to capitalize on all that information, that maybe we're hurting progress in our field by always going for the best model. Anyways, but
well, and the second thing I wanted to say is that in Bologna, so yes, there is a church, our main church, San Petronio. There is a meridian line, and it is the longest meridian line in the world, and it is one of the first places that provided experimental evidence, or I guess I don't know, other observational evidence outside of Brache's data on the proof of Kepler's laws. So it's very exciting. If you ever get a chance to visit Bologna,
I didn't know that. Okay.
Yes, so it's a very cool thing. Cassini himself designed it. So the Italian astronomer. So with that, I want to join me in thanking Rich. On Thursday, we have Q&A. So I know we did not have enough time for all of your questions, but I want to encourage you, either if you can't make Thursday, send them to me, send them to Monica, and we will moderate that discussion. But I hope that we'll be able to see you on Thursday. And Rich, again, I want to really thank you for this. This is fantastic and really just right exactly where I was hoping today's conversation would kick off. So thank you so much.
All right, thank you. And feel free to send questions and we can talk about them on Thursday.
All right. Thanks, everybody.
All right.
Buonasera.
Bye.